Hello, guys, and welcome to Advent of Cyber 2022, Day 8. And today's room is about smart contracts and blockchain. This is a very interesting room, and I am very happy that TryHackMe has actually introduced some of blockchain and some of blockchain technologies into this Advent of Cyber. It is a very hot topic nowadays and a very dear topic of mine. So the name of the room is Last Christmas I Gave You My ETH, as from ETH from Ethereum, the Ethereum coin. So let's get started. So after it was discovered that Best Festival Company was now on the blockchain and attempting to mint their cryptocurrency, they were quickly compromised. Best Festival Company lost all its currency in the exchange because of the attack. It is up to you as a red team operator to discover how the attacker exploited the contract and attempt to recreate the attack against the same target contract. So learning objectives are explain what smart contracts are, how they relate to the blockchain, and why they are important. Understand how contracts are related, what they are built upon, and standard core functions. Understand and exploit a common smart contract vulnerability. So let's get started, guys. So what is blockchain? One of the most recently innovated and discussed technologies is the blockchain, and and its impact on modern computing. While historically it has been used as a financial technology, it's recently expanded into many other industries and applications. Informally, a blockchain acts as a database to store information in a specified format and is shared among members of a network with no entity in control. So it's completely decentralized. By definition, a blockchain is a digital database or ledger distributed among nodes of a peer-to-peer network. The blockchain is distributed among peers or members with no central servers, hence decentralized. Due to its decentralized nature, each peer is expected to maintain the integrity of the blockchain. If one member of the network attempted to modify a blockchain maliciously, other members would compare it to their blockchain for integrity and determine if the whole network should express that change. The core blockchain technology aims to be decentralized and maintain integrity. Cryptography is employed to negotiate transactions and provide utility to the blockchain. But what does this mean for security? If we ignore the core blockchain technology itself, which relies on cryptography, and instead focus on how data is transferred and negotiated, we may find the answer concerning. Throughout this task, we will continue to investigate the security of how information is communicated throughout the blockchain and observe real-world examples of practical applications of blockchain. So, introduction to smart contracts. A majority of practical applications of blockchain rely on a technology known as a smart contract. Smart contracts are most commonly used as the backbone of decentralized finance applications to support a cryptocurrency on a blockchain. DeFi applications facilitate currency exchange between entities. Smart contract defines the details of the exchange. So smart contract is a program stored on the blockchain that runs when predetermined conditions are met. Smart contracts are very comparable to any other program created from a scripting language. Several languages such as Solidity, Viper, and Yule have been developed to facilitate the creation of smart contracts. Smart contracts can even be developed using traditional program language such as Rust and JavaScript. At its core, smart contracts wait for conditions and execute actions similar to traditional logic. Functionality of a smart contract. Building a smart contract may seem intimidating, but it's greatly contrast with core object-oriented programming concepts. Before diving deeper into contracts functionality, let's imagine a contract was a class. Depending on the fields of information stored in a class, you may want individual fields to be private, preventing access or modification unless conditions are met. A smart contract's field or information should be private and only accessed or modified from functions defined in the contract. A contract commonly has several functions that act similarly to accessors and mutators, such as checking balance, depositing, and withdrawing currency. Once a contract is deployed on a blockchain, and this is very important, another contract can then use its functions to call or execute the functions we just defined above. If we controlled contract A and contract B wanted to first deploy 1 Ethereum and then withdraw 1 Ethereum from contract A, contract B calls the deposit function of contract A. Contract A authorizes the deposit after checking if any predetermined conditions need to be met. So here's the diagram where contract A has a total balance of 20 ETH, contract B balance of 1 ETH, and contract B deposits 1 ETH in it. So contract B calls the withdrawal functions of contract A. Contract A authorizes the deposit if the predetermined conditions for the withdrawal are met. So withdraw, total balance of 200 ETH, 1 ETH, conditions, balance is not empty. Send ETH to contract B, and now the balance is 0. Contract B can execute other functions after the Ether is sent from contract A, but before the function resolves. So withdraw, other call, condition balance is not empty, send ETH to contract B, and contract B's balance is now 0. I will point out one actual aspect of smart contracts that it was not mentioned here, that it is they are not changeable. So cybersecurity and security of software is all about updates and updating vulnerabilities. Unfortunately, because that is very useful as well, it is not possible to update a smart contract. Once it is deployed on a blockchain, that's it. It is deployed and it is unchangeable. So that is a very, very particular aspect of programming a smart contract that you have to keep in mind. So how do vulnerabilities in smart contracts occur? Most smart contract vulnerabilities arise due to logic issues or poor execution handling. Most vulnerabilities arise in functions when conditions are insecurely implemented through the previously mentioned issues. Let's take a step back to contract A. In the previous section, the conditions of the withdrawal functions are balance must be greater than 0, and you will send Ethereum. At first glance, this may seem fine, but when the amount to be sent, when is the amount to be sent subtracted from balance? So it is subtracted after it is if it is sent. So if you check right here, referring back to the contract diagram, it is only ever deducted from balance after the Ethereum is sent. Yes. Is this an issue? I don't know. Let's check it out. The function should finish before the contract can process any other functions. But if you recall, a contract can consecutively make new calls to a function while an old function is still executing. So that yes, indeed is a problem, because contract B can make several withdrawals before the balance is updated. An attacker can continuously attempt to call the withdraw function before it can clear the balance. Yes, this means that the predefined conditions will always be met. A developer must modify the function's logics to remove the balance before another contract call can be made or require stricter requirements to be met. The reentrancy attack. In the above section, we informally introduced a common vulnerability known as a reentrancy attack. Reiterating what was covered above, reentrancy occurs when a malicious contract uses a fallback function to continue depleting a contract's total balance due to flawed logic after an initial withdrawal function occurs. We have broken up the attack into diagrams similar to those previously seen to explain this better. So here we have assuming that contract B is attacking contract A. Contract B will execute a function to deposit, then withdraw at least 1 ether. This process is required to initiate the withdrawal function's response. So attack function require value greater than or equal to an ether, so it deposits 1 ether. Withdraw all ether from account balance. So require balance greater than 0, send the account balance to the contract that requested the withdrawal, set the contract balance to 0. Note the difference between account balance and total balance in the above diagram. So the account balance is the current balance, and the storage contract separates balances per account and keeps each account's total balance combined. We are especially targeting the total balance we do not own to exploit the contract. So require value greater than or equal to 1, deposit 1 ether, and again withdraw all ether from the account, and then send. It then sends the account balance to the contract that requests the withdrawal. At this point, contract B can either drop the response from withdraw function or invoke a fallback function. So this is an infinite loop where it executes a fallback function, withdraw all ether from account balance. So it will keep withdrawing. A fallback function is a reserved function in Solidity that can appear once in a single contract. The function is executed when currency is sent with no other context or data. For example, what is happening in this example. So it is just a withdrawal of 1 ether. The fallback function calls the withdraw function again, while the original call to the function was never fully resolved. So the first withdrawal full execution was not complete. Remember, the balance is never set back to 0, and the contract thanks of ether as its total balance when sending it, not divided into each account. So it will continue to send currency beyond the contract's balance until the total balance is 0. So it always thinks that the balance is 1, and in this case, and it will, or that it's just not empty, and it will just keep approving the transaction. Because the withdraw function sends ether with no context or data, the fallback function will be called again, and thus an infinite loop can now occur. Now that we have covered how this vulnerability occurs and how we can exploit it, let's put it to test. We have provided you with a contract deployed by a Best Festival company in a safe and controlled environment that allows you to deploy contracts if they were on a public blockchain. So practical application, we have covered almost all of the background information needed to hit the ground running. Let's try our hand at actively exploiting a contract prone to a reentrancy vulnerability. For this task, we will use Remix IDE, which offers a safe and controlled environment to test and deploy contracts as if they were on a public blockchain. Download the zip folder attached to this task. We've done that, and open Remix in your preferred browser. We have provided you with 2 files, one gathered from the Best Festival company used to host their cryptocurrency balance, and another malicious contract that will attempt to exploit the reentrancy vulnerability. Both contracts are legitimate Solidity contracts, but no need to worry if you need help understanding the program syntax behind each. They follow the same functionality and methodology we covered throughout this task, just translated code. Get familiar with Remix environment, so it will explain a little bit of Remix. Let us check the files. All right, this is the Remix environment. So deploying and interacting with contracts, importing the necessary contracts. To get started with the task, you will need to import the task files. To do this, navigate to File Explorer, default workspace, load a local file into the current workplace. So let's workplace, create new folder, upload. So let's upload a file. Let's upload both of them. All right, so This is readable. We will store the target's contract to exploit in state variable called ether store. So this is the attack. This is the main contract, ether store. Mapping public balances, internal F4, internal strings. It is using hard hat framework. So we have a deposit function, which adds the value sent from the message to the balance of the caller of the function, of the caller's address balance. We have here an append function, which takes a lot of parameters and returns a string of ABI encoded of all of these parameters. This must be used in one of the other functions. Yes, here it is. It is outputted at the end of the withdraw function that stores the balance of the message sender. It requires that such balance is greater than 0. So very similar to the diagram that we have analyzed, and takes the value sent, requires that that the value is indeed sent, so it is true. Otherwise, it failed to send the ether to the requested account, and it sets the balance of the sender to 0. All right. Weird. Get balance, and this is a simple function that returns the balance of the caller's address. Let's now check the attack.sol. So ether store, public ether store. So it is storing the contract, this contract's address. Doing a construct the ether store equal to this one's address. This is provided when deploying this contract, so it does not appear. The address of this contract, it does not appear here. Fallback is called when ether store sends ether to this contract. So here we have the fallback function that if the address of the ether store balance is greater or equal than 1 ether, then we will execute the withdraw. Function attack external payable, require that message value is greater than 1 ether. It will call the ether store function deposit, passing 1 ether to it, and then it will call the withdraw function. Helper function to check the balance of this contract. So, and then we have a get balance function again. So pretty straightforward, really simple contract. So let's check out what they want in here. They will probably want us to deploy the contracts in a simulated environment. Deploying and interacting with the contracts. Actually, let's start with this one. So compiling the contracts. The next step is to compile the contracts, navigate to the Solidity compiler, select this version right here from the drop-down compiler menu. Now you can compile the contract by pressing the compile button. So where is that? Navigate to Solidity compiler. Yes, 8. The version is .10. So which is the same one presented in the contracts, and we can now compile the contract, the contracts. So it is compiling. Warning. So I believe it was compiled, yes. Yes, so Now you can compile the contract by pressing the compile button. You can ignore any warnings. Deploying the interacting with contracts. Now that we have the contracts compiled, they are ready to be deployed from the deployment tab. To the right is a screenshot of the deployment tab and labels that we will use to reference menu elements as we move throughout the deployment process. First, we must select a contract for deployment from the contracts drop-down, label 6. So let's go to the deployment tab. Is it this one? Yes. We have the ether.store contract. Now that we have the contracts compiled, let me first compile the other contract. I don't know if it is required, but let's do it. It is warning us that so this is the job of Remix. It is warning us that it has a payable fallback function, but no receiver either function, considering adding a receiver either function. All right. Now that we have a contracts compiled, they are ready to be deployed. Yes. First, we must select a contract for deployment. For the from the contract lockdown, we should deploy the ether store contract on or target contract to begin. From deployment, you only need to press the deploy button. All right. Deploy. Currently, you have no contract instance to interact with. Really? I have this one. Deploy. And it was deployed? Yes? Yes, it was deployed. We can now interact with the contract underneath the deployed contract subsection. To test the contract, we can deposit ether into the contract to be added to the total balance. To deposit, insert a value in the value box. Label 4. And select the currency denomination at the drop down under label 6. Under label 6. Once setup is complete, you can deposit by pressing the deposit button. Okay, so to deploy the attack.sol contract, we will need to provide a parameter to its constructor, which is the address of the ether store that we have previously deployed. So we can copy the contract of the ether store contract and pass it right here on its constructor parameter, and we can now deploy it. So the contract was deployed. And now we can confirm that the contract was deployed. An attack function can be seen. Yes, it can. Right here. Yes. Execute and interact with the contracts function. Note that most functions require some form of value input to execute a function properly. So let's put 1 ETH of value and run the function. The function is running, and voila. So we have successfully done the attack transaction, and we've received these 2 flags. All right. So if not already completed, download the zip folder. We have already completed that. What flag is found after attacking the provided ether store contract? And this is the flag provided. So are you up for a little challenge to celebrate day 8? Try your hand at this easy challenge. rooms maybe later, guys. So I hope you guys have enjoyed. It was a really cool room. I really enjoyed it. Very, very informational about the blockchain and smart contracts in general. It also showed us a smart contract development environment, which is Remix. um, very useful, very lightweight. You can use it in your own browser. And it showed us some blockchain security with a small and easy vulnerability. And I hope you guys have enjoyed. Merry Christmas, everyone.